To I forget about that every time. Welcome everybody to the latest installment of the Nano at Tech seminar series, sponsored by the Institute for Electronics and Nanotechnology here at Georgia Tech. My name is David Gottfried. Before I introduce today's speaker, just a quick announcement about the next seminar, which will be held just 13 days from now, 2 weeks, but on Tuesday, a regular day, on February 8th. And the speaker will be Professor Martin Morigal from the School of Physics here at Georgia Tech. And we are planning to be back in person for starting with that seminar, starting in February. So we'll be meeting in the Marcus Nanotechnology building, and lunch will be served. And of course, if we need to pivot from that at the last moment, we will do so. So it's a real pleasure to have today Professor Alper Erturk from the School of Mechanical Engineering here at Georgia Tech. Alper got his bachelor's and master's degrees in mechanical engineering at Middle East Technical University in Turkey before getting his Ph.D. in engineering mechanics at Virginia Tech. He also did a postdoc at Virginia Tech before coming to Georgia Tech in 2011, where he is currently the Woodruff Professor of Mechanical Engineering in the Woodruff School of Mechanical Engineering. He's won a number of awards, including NSF Career and several from the American Society for Mechanical Engineering. And in addition, he is a fellow of ASME and SPIE. And with that, I will turn it over to Alper for his seminar.
Thank you very much, David, for the invitation and for the kind introduction. I understand this is loosely centered around nanotech, so I may be the loosely connected person to nano stuff, but I hope it will be hopefully useful to the audience in one way or another. So for that, I wanted to cover a number of things we do in my lab. So we do both experimental and theoretical research in various problems pertaining to dynamics and acoustics of passive and active structures. So it could be purely passive conventional structural problems all the way to problems involving actuators, sensors. I work a lot with piezoelectric materials, different types of piezoelectric materials, but I'm not a material scientist, so we're more on the structural design side and leveraging various concepts. So this slide, in the context of the title, gives an overall idea of the range of domains, like in terms of frequency or scale we work on. Go all the way from a few hertz, where we have piezoelectric actuators in bio-inspired robotic research. I hope you can see my pointer. And we go all the way to problems of high-frequency ultrasonic. High frequency in the context of someone like me whose core training is vibration and acoustics. High frequency is like anything megahertz, and so I'm not referring to gigahertz. So like megahertz to gigahertz, tens of megahertz region these days, we are looking into ultrasonic power transfer. In between, there's a lot of problems, even involving biomedical problems. So quick acknowledgements here. A number of my past and current students, some of them are faculty. Sherifa is teaching at Michigan Ann Arbor, assistant professor. Shima at Virginia Tech, about to get tenured there, also assistant professor. And my postdoc just moved this January to Stevens Institute of Technology, again on tenure track. And a number of other people like Ahmed, my current postdoc, and Etu and others. So I'll basically feature some results from their research. Also, I acknowledge my co-PIs and collaborators in some of these projects. So I'll start from relatively low frequency stuff. We've been working on problems related to harvesting energy from vibration. So there's a number of different ways, obviously, for energy harvesting. But again, in my domain, we work on vibration energy harvesting. So again, in the context of this kind of seminar, I imagine many of you would be more into transducers already. So in case, you may already be familiar again, so that's why I didn't put too much material, but basically piezoelectricity is a coupling, electromechanical coupling in certain ceramics and crystals. So it doesn't obviously happen in every single types of materials, but when it happens, it's a pretty cool effect. So you can have the so-called direct effect. When you have a piezoelectric material, if you apply some mechanical deformation, you get some electrical output. Like if you put some surface electrodes, you have some potential difference. The same material, if you apply some potential difference, you see mechanical deformation. So that's the converse effect. These were discovered back in late 1800s, 1880 and 1881. Again, you need to have typically a specific type of you need to have this non-centrosymmetric arrangement in the microscopic scale, just like in silicon dioxide here in quartz. When there's no applied stress, the centroids of these silicon and oxygen atoms are coincident, but in response to mechanical deformation, so there is some symmetry breaking there that results ultimately in some macroscopic and significant electric potential difference, such that you can easily get like a few volts and even sometimes hundreds of volts voltage level. So again, you could do that. This is the case of mechanical deformation, just like the animation I put from Wikipedia, and you have some voltage readout, or you may be applying some voltage input and you get mechanical deformations. Some of the fiber-based actuators with interdigitated electrodes we used in underwater locomotion, for instance, I'll talk about those. But yeah, I mean, you have different modes of piezoelectricity depending upon whether if your mechanical deformation and the electric field are orthogonal, like in this manner, main strain or stress direction is one direction, electric field is in three directions, this is 3-1 mode, and if they are coincident, it's the 3-3 mode. So we use actually both of those effects. You can make a bender for actuation, harvesting, and so on. The kind of busy slide just showing you examples of, I haven't put in order to be able to cover a number of topics, I haven't put too much of introductory slide on piezoelectrics, but we have worked on a number of topics, and there's a number of actually applications for energy harvesting. Obviously, in the future, also with the Internet of Things, you can even expand this domain, but I haven't again put too many such motivation slides. When I first started at Georgia Tech, I had an SPIR project for Navier for energy harvesting at the root of the helicopter blades, because you have significant vibrations there, and you want to do health and usage monitoring, like the health monitoring of the blade. So can you make it entirely self-powered so that you leverage some of the vibrations there instead of passing some wires, like a feed through of the wires? So there could be that sort of problem where you have some frequencies, or it could be a vibroacoustic problem in a jet engine environment, or it could be totally much lower frequencies, even less than a hertz in civil structures, where again there is potential applications because you have all sorts of wireless sensors in all these problems in charge of various things: structural health monitoring, health and usage monitoring, just like the sensor network shown here in this structure. And every once in a while, variable electronic companies approach with some either a proposal solicitation and this and that for ultimately to make self-powered, let's say, fitness tracking devices and this and that. So we try to quantify how much power you can harvest those. This here, quick example from one of my former graduate students, where he was actually a master's student. I co-advised with GTRI on a NASA project these were deployed at the Kennedy Space Center entirely for entertainment purposes. So there's a number of things that you can do with this stuff. So to jump right away into what I want to talk about in terms of energy harvesting concepts. So as you saw in the previous slide, you could have an application of with frequencies, a few hertz, tens of hertz, hundreds of hertz, or thousands of hertz. So when you design a vibration energy harvester, which is typically a cantilever with a transducer, in this case, in my case, in my lab's case, most of the time it's a piezoelectric transducer. So when you make a resonant device, it will give you the maximum power output at a certain frequency. But the moment you deviate from that frequency, especially if you have a high quality factor design, and that's what you want to have most of the time for the largest electrical output, if you deviate from the resonance condition, your power output diminishes, basically substantially. And it may happen for many reasons. I mean, in the application, your excitation frequency might be changing, or due to environmental conditions like a temperature change or so on, your resonance frequency may shift and deviate from the excitation frequency. So that's why, back around 2009, myself and some other people introduced leveraging concepts from non-linearities for bandwidth enhancement. So now it's a domain by itself. I'll try to show you examples of that. So if you take a cantilever like this, one of the easiest ways to introduce non-linearities is most of the time, in my case, a microscopic scale, like a millimeter, centimeter scale. So it's not a problem to work with magnets and all that. But I'll also show you what is out there in terms of MEMS devices leveraging non-linearities, especially in electrostatic energy harvesters. So why we like magnetic attachments? Because magnetic force phase dependence is right away nonlinear. So you could make this so-called a hardening stiffness, softening stiffness to deviate from linear spring behavior, or even more exotic is bistable. So you can kind of if the south and south poles are facing each other, there's some proximity of the magnet, this beam will be buckled to one side, and then you have two stable equilibrium positions. So that's bistable. So in case of monostable, if you have a hardening stiffness, your linear resonance is bent to the right. If in case of softening stiffness, which would, again, it's a matter of like just arranging some magnets or doing some other, again, magnetic way is not the only way. I'm just showing this because it's one of the easiest. Or you can have softening. In both of these cases, if you want to talk in terms of bandwidth, let's say from the half power points, let's say you have a certain quality factor, you can go from the quality factor to the half power points bandwidth. So that bandwidth seems to be enhanced when you introduce non-linearities. Now, bistable is a double well potential problem. If, in case any of you are familiar with that, that's much more exotic. It can pretty much show all the interesting nonlinear dynamic phenomena. It can give you chaotic vibrations. So you're basically going from, if you can follow my pointer, like say your resonance was something, oops, sorry about that. You had this original narrow band resonance. You can go to a much wider frequency response. Your peak amplitude might be lower than what you would get at a single frequency of a linear resonance, but you have a wider range of frequencies where you get some usable electrical output. Yeah, this was the configuration I had looked at, like a piezoelectric patch to magnets. Like this is back in 2009. Now, again, in the nonlinear energy harvesting domain, there is hundreds and perhaps thousands of papers already. So you could like modify that magnet arrangement to get something like this, or in the bistable setting. So in all these configurations, you have two stable equilibrium positions. You can just simply come up with a buckled beam. I'll show you a MEMS example of this kind of arrangement in a minute. So you could have two stable equilibrium positions. So when that's the case, if I can go back to previous slide in a minute, bistable is the red one. So even in static loading and unloading, so you have the so-called snap-through behavior. So this is the loading, this is the unloading. So it won't follow the same path. There will be a hysteresis, even in the static behavior, and dynamics is even more complicated, and it will give you chaos and so on. Or monostable stuff. Various examples here. This one from my colleague Brian Mann at Duke University. This was also like 2009-ish paper on electromagnetic type. Let's say again, you could create a magnetic levitation here. This is a magnet. These are two magnets here, or like just iron maybe. You could create like an interaction here for this for the levitation of this proof mass, and there is a coil outside. So in response to mechanical base excitation, you could create some like nonlinear stiffness due to the magnet interaction. Anyway, so in a nutshell, like to give you an overall idea, again, these are microscopic scale, centimeter scale devices. These are your typical chaotic vibrations. So here's experimental data. Like instead of getting, in the absence of those two magnets that make it bistable, so you're going from this kind of FRF to like a wider frequency response where you can harvest a lot of power. So if you're into math, there's not much equations. I'm also like on the modeling, dominantly on the modeling of this stuff, and like an applied math sort of person. That may be the reason most of the internal seminars I gave at Tech were the math department multiple times to the applied math people there. So your stiffness is modified in this manner. Okay, so you have two like plus minus one are equilibrium positions, they are stable, and 0 is no longer a stable equilibrium. Again, I'll show you a MEMS example of that. At the microscopic scale, we worked on various types, like you can optimize the piezo locations on this buckled carbon fiber plate. So these are like different lamination conditions of a plate setting. So you can, bond asymmetric laminates go to curing temperature. When you go back to room temperature, because of the thermal expansion coefficient differences, it will buckle, and you have again a bistable configuration. And in a nutshell, you go from if you look at the power output frequency response, you go from a narrow resonance that you would have for an ordinary square plate, you go to a rich frequency response in the similar kind of device dimensions. We also make use of, it doesn't have to be bistable. We also use monostable configurations like a hardening stiffness. This kind of configuration is especially useful for if you have low G vibration levels. Like sometimes you don't have those. In previous slide, it was like 0.5 G. G is gravitational acceleration amplitude. Okay, so we try to quantify input vibration acceleration level in terms of like gravitational acceleration. So like if you have milli G, like you want a much more flexible device. I'll show you a MEMS counterpart of this in a minute. And if you have a strongly nonlinear system like this one more remark before we move on to the examples in the next slide. So you do have a primary resonance. This is where if this was a linear spring behavior, you would have this like narrow band resonance here. So we're introducing the hardening nonlinearity and wider frequency response. And this is an electromechanical system, so resistors. By the way, like these dots markers are solid lines are modeling by the method of harmonic balance. So the thing I wanted to talk about is, let's say you have dominant quadratic and cubic nonlinearities here. The moment that is the case, you have the so-called secondary resonance. So 14 hertz is your primary resonance, but if you excite at because you have quadratic nonlinearity, if you excite at 7 hertz, you still get interesting behavior. If you excite at 1/3 of 14 hertz, which is around here, you still get interesting behavior. You have the so-called nonlinear frequency up conversion, which could be useful, let's say, for MEMS purposes. Myself and others claim that, but nobody ever implemented at MEMS scale. I mean, here's what I'm trying to say. Let's say this is an example from, I think, S.G. Kim's group at MIT, one of the first MEMS piezoelectric energy harvesters. This would be a thin film PZT with this interdigitated electrodes on one side. So let's say the fundamental resonance first banding mode is around 13 kilohertz. One of the problems in MEMS energy harvesters is you don't have ambient vibrations typically in most cases, unless you have some machine component or something that produces that sort of frequency. You don't have much energy there. Most of the energy is here on the order of a few hertz or maybe 1,000 hertz. So you could introduce such secondary resonances let's say to excite those frequencies and get response at the primary resonance. But again, nobody has done that because it's not that easy to. There's a few people doing a very successful integration of these nonlinear concepts. A good example is a good colleague from Norway, Professor Einar Halvorsen, and he collaborates with Berkeley very often. This is like that amp-shaped structure I showed you, but more for softening purposes. So he leverages, it's an electrostatic capacitive device. So as you can see, instead of getting a narrow band high quality factor resonance here, it gets a nice softening behavior. These are different bias voltage levels showing the frequency bandwidth enhancement. And then later on, he implemented. He was probably the first. If you think of our bistable paper in 2009, this is pretty actually the early MEMS nonlinear literature to integrate a bistability. So now if you look at the springs holding, this is your proof mass. I hope that's clear. Okay, so in this case, this is your proof mass. So if you look at the springs, okay, so these cantilevers are in spring constant, so a clamp guided manner. So you can imagine that this is nicely compressed here. So you have a bistable setting. So you can tell that from the spring displacement, force displacement behavior of the spring. So you have your again, if you do the loading, unloading, there's that hysteresis and snap through behavior. And one more time. So you're going from a resonance like this to all the way to an enhanced bandwidth. So maybe you're already familiar with some of these stuff, or maybe you have seen other applications just like in MEMS, NEMS, very sensitive mass sensing using bifurcations. So instead of relying on linear resonance frequency change, you can again rely on introducing a nonlinear bifurcation for a larger sensitivity or a range of frequency. So again, there is a number of, some of these I won't spend too much time, but we try to introduce, let's say, those nonlinearities. They are intentional nonlinearities we deliberately introduce, but piezo can also have its material nonlinearity, which is usually manifested in the form of material softening. So the challenge becomes, and of course you can have nonlinear damping, internal solid damping, or if it's a flexible structure, it could be external fluid structure interaction kind of damping. Again, you could encounter that in MEMS concepts too. That's why you have vacuum packaging and so on. These are usually, the reason I'm showing this slide is fluid damping is just even in linear quality factor device, in nonlinear setting as well, it's quite detrimental. The size of the bandwidth that you're getting from nonlinearity is shortened when you have larger fluid damping. And also we try to make distinction carefully, when you have a quadratic damping, when we analyze, is it an internal quadratic damping, due to internal friction in the material, or is it due to external damping and so on? And again, it could get even wilder, those nonlinearities. Now we're talking about literally inherent nonlinearity, because I have this cantilever that I want to use it as a nonlinear actuation. Okay, it could be a flapping wing, it could be a bi-inspired swimmer's tail or something. Now for moderate large deformation, you have geometric hardening, inertial softening in any passive structure. They take any linear elastic Hookean kind of elastic material, something like this guy here. Okay, tempered blue steel, spring steel will give you minimum plasticity in large deformation. That's why we like it in nonlinear experiments. What you will see in an ordinary cantilever is a hardening nonlinearity. Okay, you can intuitionally tell as well. If you take a cantilever like a ruler and give some force, look at the displacement, after some displacement levels, it will start to resist. It will require more force for unit displacement. That's called hardening. So like this is what you expect, but now you make a cantilever out of these fiber-based piezoelectrics. This was invented in early 2000s at NASA Langley Research Lab. They were tested actually where I did my Ph.D. in the first decade of 2000s, and then I worked a lot when I started Georgia Tech on non-linearities of this stuff. That was actually my career project, like to look into the complex non-linearities of this stuff, and to integrate into like bio-inspired streamers and so on. I mean, a cantilever that is passive, a cantilever that is piezo. So when you increase the amplitude, your resonance is totally messed up. So when you try to derive these things, and this is model versus experiment when you do a rigorous analysis. So it takes like, if you want to use them at the extremes where they're more interesting to use, obviously large voltages in actuation or large base excitation, there's a lot of things being pronounced. So those are inherent nonlinearities, okay? So again, although I know this is like loosely connected to nano, but I thought I would still insert some stuff. We looked at in the past. So first of all, one of my collaborators, Professor Pradeep Sharma at the University of Houston, he is a computational mechanics guy. He does a lot of atomistic simulations, also continuum simulations. So they had looked into in 2008 or so the effect of strain gradient induced polarization. That's called flexoelectricity. He's not the person who invented that, so you could go back to Soviet literature in 1950s, 60s. So what this says is like, even if you have an ordinary centrosymmetric configuration, like I think in the coming slides I will talk about strontium titanate, okay? So like it's not a non-centrosymmetric material like you would require in a piezoelectric material, right? So if you are talking about even this kind of symmetric arrangement, if the thickness level is low enough, you're going to have symmetry breaking due to non-uniformity of deformation. Okay, or other people work on axial deformation, like with pyramid, cube-shaped structure. So you could have again non-uniformity in deformation, just like having a curvature here, or you could have like geometric non-linearity, uniform deformation that will still give you or uniform loading that will still give you a gradient. Anyway, so this will be interesting only if the thickness goes below 10 nanometers. That's why there is not much doable in terms of very rigorous experiments to capture the behavior on individual nanocantilevers. So anyway, like Pradeep had approached me sometime, and then like we put together to quantify what is how could this be used for energy harvesting. So I mean, this should be there in a lot of materials that you are looking at inherently, but like not. There hasn't been much of like rigorous effort to quantify, and I'm still like, if any of you guys in the audience, or if someone who looks at the video later on finds it interesting and finds some ways to kind of like experimentally test and identify this, we develop lots of frameworks on these things. Okay, so let's say if you take again a centrosymmetric configuration like a polyelectric material in room temperature, like strontium titanate, and again, you will have normally, again, it's not piezoelectric, it's not ferroelectric in room temperature, but if you do go down to low enough thickness levels, you're going to get some polarization and significant electromechanical coupling comparable to like a PZT in a microscopic scale. So we have frameworks for that. At some point, we did. I did commit some kind of funding on this stuff to one of my graduate students. We acquired some barium titanate, which is already ferroelectric and piezoelectric. So in this sort of BTO setting, you have some piezoelectric constant, okay? Some electromechanical coupling, even microscopic scale, you do have some piezoelectric constant, but that gets to be enhanced. So these three graphs are showing that like just what is due to piezoelectric effect and what is due to the bi-flexoelectricity itself and the enhancement. Therefore, when those two are combined in the coupling coefficient, when you go down to very low thickness levels, again, you would have to be on the order of like ideally less than 10 nanometers thickness, but at least you would still observe, like if you are 10, 20, 30 nanometers thickness, you would still observe something. Anyway, so yeah, we were playing with barium titanate nanowires and so on. It would take like, we at some point gave up, I think partially because I'm not necessarily an expert on these things, but like also I think it's a very demanding experiment to isolate an individual nanowire. But I'm, again, if any of you finds this stuff interesting, we could talk. So switching gears a little bit, like you don't always have direct vibrational energy to harvest in the problems like where you need to power some small electronic component or a wireless device. You may have airflow, like or water flow. So kind of the hydroelastic instabilities we normally don't like in real large conventional structures like flutter or buffeting, and all those are useful for energy harvesting. These are some of the early generation stuff. In aircraft wing, you have a bending mode, torsional mode, typically coupling to create like instabilities and limit cycle oscillations. So why not introduce, let's say, a plunge degree of freedom and a pitch degree of freedom? Like a cantilever is one plunge stiffness, and you can introduce an airfoil here, and there's a piezo. So at certain critical speed, this will give you limit cycle oscillations. So there's different types. I'm just directly showing you what we do with polymer piezos like PVDF in flexible configurations. Just like this, the way this goes unstable is just like a flag. Okay, and after certain critical speed, you have some nonlinear limit cycle oscillations. The reason I particularly show you this example is because there's a challenging problem there. This is not a standing wave, it's like a propagating wave. So it's not like it looks like a second banding mode, but it is not. So it's a propagating wave. So the question becomes, how do we do the segmentation of the electrodes? So we make some effort to optimize where to do the segmentation so that instead of using, so this is PVDF, right? Like we can cut and bond, and there's a thin steel substrate underneath. So instead of like just doing the continuous and getting some cancellation of the charge outputs due to the inflection point and the curvature sign change, so if you collect them separately and do the segmentation, you get much larger power output. And there is nowadays we look at the inverted flag problem. This video may be a little fast, so maybe I'll show you a slow motion here. Inverted flag meaning like what we call this leading edge becomes the trailing edge. So like instead of flow coming from the right-hand side here, it's actually coming from the left-hand side. Or let me show this simulation from my collaborator is Professor Korsholi on these. Like he does full Navier-Stokes simulations. So you can get that kind of response, or you could get these like one-sided response depending upon where you are in terms of flow speed. The reason I'm showing you this one is like it reduces the cut-in speed, like minimum speed of like these nonlinear limit cycle oscillations substantially. So you don't have to require large flow speeds to trigger your hydroelastic energy harvesting device. We also work on like other fluid structure interaction problems. So these are stuff, as you see, like mostly on the order of a few hertz and so on. Gradually, these frequencies will increase as I show other applications and problems in our research. This is a first generation piezoelectric robotic fish. Actually, it's the first untethered piezoelectric robotic fish in the literature. Which, it has all the amplifier and battery and everything in it. We looked at like a lot in terms of like this basic semi-empirical modeling, like what is the effect of hydrodynamics in terms of inertia and drag coefficients. Like for those of you who may be familiar with like AFM cantilevers in fluid, like John Sather's work, like that sort of like narrow cantilever problem typically has an inertial coefficient of unity. But what I'm referring to here is like we are looking at aspect ratios comparable to each other. So your inertia and drag coefficients might be, they're not very trivial to find because the shed vortices from the two edges become comparable with itself. For that sort of thing, in my lab, we either I'm not a fluid dynamics person, I'm more on the structural. For fluids, we either do semi-empirical stuff like the Morrison's equation in the previous slide, or we collaborate with CFD people like Alex Alexiou here, who does the CFD part of the thing. So we can understand also with increased amplitude why experimental data shows like a nonlinear inertia coefficients and so on. We have actually on these sort of like swimmer stuff these days, pending Muri for studying fish schooling and complex hydrodynamic interactions in a network of schooling fish. So we'll see probably the outcome in the next weeks or months. So this is, it's the second generation, latest generation on my lab on robotic fish. We also use these things for energy harvesting purposes. So again, you're looking at and seeing the frequency still to be on the order of a few hertz. But that's what you have also in biological fish. It doesn't like most fish. This is trout, it's representing trout, like the aspect ratio and dimensions. So your oscillation frequencies are on the order of a few hertz. So if you put a bluff body, let's say this fish is resting somewhere and you have some bluff body, or the main body of the fish could be like a bluff body, if you like, could stop and try to harvest energy from flow. So that's kind of what you're looking at in this slide. And we are looking at especially around the first mode neighborhood. The way it works here is shed vortex frequency here will depend on the diameter and of this bluff body and the flow speed, of course, and the Stroll number for this kind of flow is around 0.2. So let's say if you want to be able to, so the first banding mode is around 2 hertz. If you want to hit like the 2 hertz neighborhood, like if you use this bluff body here, which is the largest bluff body, around this flow speed, it will hit the resonance, and you can see that like that will give you the maximum power output. So this is again a typical design problem to create resonant dynamics. But yeah, some of our current interest is to go to like multiple piezoelectric elements to do complex motions. Like turns out biological fish doesn't just do bending, so like bending, twisting, and all that is what we're interested to extend in our next generation robotic fish stuff. So switching gears a little bit, gradually going to higher and higher frequencies. There's this domain of metamaterials. I'm sure many of you may have heard. There's electromagnetic, plasmonic metamaterials. There's acoustic elastic metamaterials. Obviously, I'm on the acoustic elastic metamaterial side. So there's locally resonant bandgap formation. Like bandgap is a range of frequencies, just like in solid state physics. I mean, it's analogous to solid state physics. So people borrow from, just like you would have in a lattice crystals, like electronic band structure, a bandgap, right? We try to create something similar in acoustic elastic metamaterials for sound and vibration attenuation or absorption. Okay? So there's a number of works here, including some of our own and including collaborations, like this is bandgap tuning in a shape numerically. I'm not going to talk about this, or this is topological with one of my colleagues, Massimo Ruzzini, who's at Colorado right now. And this is time modulation. I'll show you specific examples on programmable stuff before I give you a little bit of motivation. So yeah, if you take a periodic structure like with resonating elements, you can create a bandgap, and again, analogous to solid state physics bandgap of electronic lattice structures that you may be familiar with. So the thing about like resonating bandgap, like resonating unit cells, is you can make tunable bandgaps for wavelengths on the for wavelengths much larger than the lattice size, as opposed to Bragg scattering based bandgap. Okay, in ordinary periodicity, you always have Bragg scattering, but like if you use resonating unit cells, you can create a bandgap at lower frequencies because you can tune it. So that's basically, if you remember, like the nature of bandgap formation in Bragg scattering is more about the lattice boundaries related, like if you like impedance mismatch, as opposed to these resonating elements here. It's more about the phase difference between main structural motion and the resonator elements. Okay, we'll go to the electromechanical counterpart in a minute. I mean, if you're interested, like if you do this, like let's say you're sending some wave, sweeping the frequency of the wave, and you will see a bandgap right now, just a little bit of evanescent wave, and then like you have no propagating waves in a bandgap, and these are typical dispersion branches for different structural configurations. And because we do nonlinear stuff, we of course, I mean, it would be surprising not to use bistable attachments also in these structures, where you do two things. So you can create a bandgap for low amplitudes where you have linear oscillations of these attachments. If you go to large amplitudes, you can trigger chaos and so on. So you have a hybrid mechanism of like linear, nonlinear. Bandgap is a linear concept, but if you go to large amplitudes in a bistable setting, you trigger chaos. So now we again, being a piezo guy, like we try to, like, again, these are off-the-shelf piezos, but we modify them in a way that like we create some unit cells and inductive shunts, and these days mostly like synthetic impedance circuits for bandgap formation, because you have a lot more flexibility when you rely on the electrical side of the problem. You could easily create a bandgap because piezo has a capacitance inherent characteristics. You put an inductor, there you go. Like you have an array of inductors with piezo unit cells. You create a bandgap. This is some frameworks, but I'll directly try to move you on to the some most recent results. You could do hybrid stuff, mechanical bandgap, electromechanical, because there are some mechanical resonators and some inductors on the piezos, and you could do multifunctional stuff. I should have a slide in the next one. Let's say, why don't you use piezoelectric elements on these mechanical resonators? So not only create a bandgap for vibration attenuation in the structure, but also harvest some of that like resonators vibrations essentially. Okay, this is in my lab, again, a long stroke shaker here, a main structure and the resonators, they have piezo elements. So we are looking at like how much power we are generating and which of the, like, so there is a certain total power, which of the resonators are producing more of the power output. and what is the size of the bandgap and all that. Now, this is the more interesting stuff. It's our first generation configuration with just seven or eight piezos. One of them is being used as the exciter, as the actuator. So you're looking at 7 piezo metamaterial domain. This is all experimental data. So we combine negative capacitance for electromechanical coupling enhancement, plus obviously inductances for resonance. So this is showing moving a bandgap around in a structure like this entirely digitally, because we don't use analog inductor components. So there is a few analog components in a typical synthetic impedance circuit, and then most of the stuff is in lab view. So you can entirely program, like this is also experimental data. You are looking at like a heat map of the resonances, and you are moving the bandgap across multiple resonances of this structure. And currently, what we have in terms of these programmable metamaterial domains using piezos, we have something around 30 unit cells. So we're using, again, one of them as an actuator, so 29 unit cells. With this domain, we can do many things. I mean, we try to do these days. This actually just got accepted a couple of days ago, physical review applied, where we gradually vary those inductances. So there's this concept of a rainbow metamaterial. Again, many of these things originate from electromagnetic metamaterial. Okay, people did show plasmonic electromagnetic counterparts of these things first. But when you take it to the elastic domain, so rainbow metamaterial is just like in the optics problem. So if you can localize different wavelengths in different spatial positions, so it's like a rainbow, like gradually varying color. So this is the elastic wave counterpart of that. So what you do is like your inductances are gradually varying. So I open a bandgap here, there at different spatial positions. So that's why, like, this is experimental data with scanning lasers after my vibrometer. This is mobile data, and this is actually simulation showing animation of the experimental data, showing the bandgap for different profiles of the inductance distribution. So you could, create the band at this frequency. The bandgap starts at this spatial position, at this frequency, at that position. So you could, like, if you were to send individual wave packets, like you would have those spatial localization of different frequencies. If in case of a continuous wave, this is what you observe, still showing that like different frequencies are being stopped at different spatial positions. And this is also interesting, by the way, for energy harvesting, because what this produces is localization of modes compared to going with a uniform inductor profile. Like with non-uniform inductors, you have this like multiple, lots of vibration modes localized, so you can enhance the power output if this is an energy harvesting problem. These stuff have also implications, just so you know, if you want, in case I should relate these things to like sensors and so on, like in MEMS. Like, take a look at this example. It's very analogous to the previous problem. So this is more of like a wave compression. So when there's this concept of an acoustic black hole. Acoustic black hole is like you're sending this wave, just like in the cosmological counterpart of a black hole. Like if you have no reflection back, just the wave keeps slowing down. What will happen is that like that wave will be amplified. If you look at this is COMSOL simulation. You get a specific inductance profile or an circuit profile over here, circuit impedance profile. So what you're doing is it's not the same problem as the previous slide. For a given frequency, I'm sending a certain wavelength, but it's being compressed due to the impedance change here. And if you look at the voltage of the piezos, it's being amplified. So these kind of concepts can be used also for signal to noise ratio enhancement. Interest of time, I can skip some of these, but there's also cool concepts of like non-reciprocal wave propagation. This could be like, people are looking these days at like the possibilities to integrate these things to surface acoustic wave devices for non-reciprocal wave propagation, or any one of the previous stuff we just talked about. So like if you create an active shunt in a way that like it produces something like a stiffness wave in a structure, okay? Like you do have like a basically space-time modulation of the shunt circuit capacitances in a way that like, let's see if this animation is gonna work. This is space-time plots. I'm exciting a, let's say, infinite beam at the center at this frequency. Normally, this is what you have in a passive structure. If you have a spatial modulation, like an inductive shunts all the way, same inductance, this is a bandgap. Now, if you have space-time modulation, you can create directional bandgaps. So at one frequency, wave propagating on one side, and it's the other way around at another frequency. So that's one of the cool areas. These are, that's a totally active concept, okay? Maybe one last on programmable stuff. Let's say you have a surface wave. people showed like this is from what you see on the upper right corner is a is on surface waves on the seismic problem. Let's say you want to protect some kind of building from earthquake, some kind of like a surface wave coming from here. Can you do a mode conversion? Let's say this Rayleigh wave, surface wave, turning into a shear wave and bury it back into the ground rather than hitting this structure over here. Anyway, so like instead of using, so they introduce this meta tree concept. But if you have piezoelectric elements on a structure like diploid, it could be some interdigitated setting. If you gradually vary, let's say this is your surface wave. If you gradually vary the phase velocity of the wave and approach and make it equal to shear wave at a certain position in space, you can do wave mode conversion. So this animation shows that. This is a surface wave coming here. So these piezo elements, they have certain inductive shunts. And as you can see, like right over here, so you can do it so you have mode conversion from surface to shear wave. Or you could do like, if you gradually vary the inductances in a way that like you can make the surface wave hit a band gap and nothing, it will be just reflected back. So this sort of domain can be programmed by just simple inductive shunts. And yeah, I seem to have put like this nonlinear stuff too. We also try to introduce nonlinearities through the circuit, like a cubic. Think about the mechanical nonlinearities I talked about earlier. What if you do like a cubic capacitance or cubic inductance? The upper one, we already demonstrated that like with analog circuit components, a cubic capacitance, there's this concept of a nonlinear energy sink. So you can do a broadband absorption over a range of frequencies. So nowadays we're playing with the synthetic circuit to make it entirely lab view based programming, like to create, let's say, a cubic inductance. So as I get close to wrapping up, so like when you look at much higher frequencies in terms of what we do in that regard, we design lots of like elastic wave and acoustic wave lens concepts. You remember the concept of refractive index or index of refraction. So when you have a wave propagating from one domain to another, basically it bends. So there's the refraction and there's the index of refraction. Just to remind some definitions here, in the optics counterpart, index of refraction or refractive index is the maximum speed of light. Let's say speed of light in vacuum, or the phase velocity in vacuum divided by phase velocity in whatever the domain you're talking about. Let's say when you talk about the refractive index for glass, 1.33 and so on. So, or like you have refractive index of water, so you get these kind of like illusions and so on. So when you try to make a lens for lamp waves, guided waves, now we're switching gears to, let's say, going to tens of kilohertz. Let's say we want to make a lens for flexural waves, the lowest anti-symmetric lamp wave mode, so that like, can I design this domain of a structure, of a thin plate, you will see in a minute, so I can get the lowest wave speed here at the center and fastest around the circumference, so you have some focusing. In the interest of time, I'm going to move on to the experimental results right away with some animation. So this is a scanning laser Doppler vibrometer. This is the scanned area back of the plate. This is the front of the plate, just machined with these blind holes of different diameters. So wave will be going slower here, faster, and there will be some focusing. Here we go. I'm going to try to accelerate this a little bit. So you see the central portion slowing down, that's the focusing. If you make the domain long enough, it will defocus and refocus. For demonstration, what we try to do is to show the signal enhancement or the focusing enhancement. We try to show it in terms of energy harvesting, because energy harvesting is always cool. Say the flat plate domain, you put a baseline piezo patch, like half wavelength size, like a circular setting that will resonate. And then you have the plane wave source at the same distance. And here I have the lens domain, okay, phononic crystal lens. So I have, as compared to the flat plate domain, I have more than an order of magnitude enhancement of the power. And you could do an omnidirectional counterpart of the same. So I will just accelerate this. Again, the domain with hexagonal unit cells is designed in a way that like you have the slowest wave speed at the center. This is experimental scanning laser Doppler vibrometer data. And you have substantial enhancement of the signal. We usually use a burst of like finite cycles rather than a continuous wave to avoid like interaction with the reflections from boundaries. And you could use like 3D printed stuff, except that like the moment you use some bonding and interfaces and soft materials, you have loss. Okay? Your enhancement of the signal or the power, the focus is not like an order of magnitude but still a factor of 3 or so. This is like we eventually, in a more recent NSF project, we translated these concepts to three-dimensional counterparts like acoustic waves, ultrasonic waves. So like both audio frequency, I'll show you in the next slide, and also like ultrasonic, like let's say in this case 100 kilohertz neighborhood. So you would design basically the variation of the refractive index profile at a given design frequency for a domain like this. This is an ordinary 3D printed PLA, and you are looking at the micro CT scan image of the unit cells. So here, the moment the underwater acoustic wave hits the lens, it is propagated in the domain of the solid of the PLA through shear waves. So this is the branches that you work with to tune the refractive index profile. I can show you, I think this is ordinary, like if you just send a plane wave, without a lens, obviously nothing interesting. But now from the opposite side, plane wave is coming and it's being focused. So that's like the animation counterpart of this experimental data. And you have like in the pressure or the voltage a factor of 2, 3, and that will translate into power by square of that. So you get less than an order of magnitude, but more than 6 or 7. This one here is the audio frequency acoustic counterpart of that. Again, you decide on a certain building block, your unit cell, and the domain is designed. So this is in my lab with a loudspeaker and a microphone, just scanning what is the pressure at the back. So again, some pressure comes from here. Again, audio frequency less than 20 kilohertz. So you put something at the focus point to show the signal enhancement. This is just a buzzer in this case, nothing optimized, because you have a fair comparison. You remove the lens, you put the lens at the same frequency, all conditions are the same. Normally with that buzzer, if you try to harvest like ordinary sound energy, like at less, at amplitudes at a reasonable dB level, you get nanowatts, that you can enhance that to microwatt power level. Let me accelerate to wrap up. So most, recent stuff in terms of power transfer. So you don't, first of all, those lenses, we use it for power transfer as well, but we also have dedicated problems of like ultrasonic power and data transfer, mostly for Sandia National Labs these days. I'll get to those right away. But communication is also a possibility by using ultrasonic waves for underwater purposes. Again, just these are some motivations of why use ultrasonic power transfer instead of the standard de facto like electromagnetic counterparts or even RF. So piezoelectric transduction can give you ultrasonic waves that can propagate and penetrate to deep implants. It could be an implanted sensor in a civil structure. It could be a medical implant and all that. So we started playing with those with one of my former Ph.D. students back in 2015 or so. Developed some models for ultrasonic transmitter receiver. I'll show you right away the most recent and ongoing stuff. We do these things nowadays for Sandia National Labs. So their standard problems that we cannot go into too much detail on is you have an enclosure like a Faraday cage. So you have some electronic components in it. So electromagnetic methods of power transfer is not a possibility. So your only means to do that, and you cannot rely on battery in a sealed setting. So your means is to use acoustic waves. So you can use some piezoelectric transmitter receiver in a thickness mode. So we're talking about much higher frequencies now, all the way up to megahertz. What we do is so first of all, both power transfer and data transfer. We try to do, and Sandia has multiple contractor universities. There's ECE people at another university, and ourselves here try to modify and design the frequency responses both for data transfer purposes. Some of you may know better than I that this bandwidth depends on this relatively flat bandwidth tells you how much, let's say, megabits per second you can send, right? But you also want some sharp resonances, maybe at another frequency for power transfer purposes. And one of the challenges in this sort of setting, when you have multiple channels, let's say I'm using this piezo in thickness mode, the moment I excite, let's say, at a certain thickness resonance at megahertz, it also produces guided waves, Lamb waves. They will propagate and create crosstalk. So phononic crystals and metamaterials are not used very often in real applications, but this is one of the real applications of creating a periodic structure here, a micro machine domain that creates a bandgap at the frequency where the power piezo tile is operating. So we try to use this stuff for blocking, let's say, or isolating power tiles from data tiles or data tiles in between them. So this is, I think this flyer was okay to use for these public purposes. This is a Faraday cage in my lab and some anodized barrier here. But to give you an overall idea, unlike energy harvesting problem where you're limited by ambient vibration amplitudes and so on, you get these microwatts, milliwatts. Here in ultrasonic power transfer, you can get watt level power output. Because first of all, you're doing this through metal, and you are, you can put whatever the power you like, okay? You may rely on battery-based operation. These days, we do these portable devices, so it's entirely DC to DC problem, but it may as well be AC to DC, so you can put whatever the power level you want. And of course, there's the communication part, like you can stream with the data transmission portion through a wall in that manner. So this is, I think, the most recent things that we have for dry contact with some magnetic attachment here. Piezo is not even bonded on the domain, so I'm going to try to accelerate just powering some LED lights on the other side of the through the other side of the barrier. Again, your power goes down when you have dry contact. We use some polymeric attachments. We are not permitted to use gel couplants, so you still get like a few watts, which is okay for this application. And you could do these things also for those lenses I showed you. If it's an underwater power transfer and communication problem, you could use those for signal enhancement. I wanted to make that, close the loop in terms of what is the use of those underwater acoustic lenses. So you can use a point source and project the signal, and then at the receiver, you may have another lens to focus the signal. I think this was the last, and I will stop. So at the higher frequency end, I happen to have this like 5-year project. We're around the second year, actually it's 2 years past, around the third year, midway. I have multiple co-PIs. I'm leading the project. Some are looking at the imaging, some on the therapy. Me and one of my collaborators who moved to Colorado, Massimo Rizzoni, we're looking at the vibration, vibroacoustic, and also guided wave side. And I'm especially on the vibration side of the domain for the purposes of, again, what can you do with vibrations? Like, we need accurate parameter identification of human skull for focused ultrasound purposes. But there's a number of challenges I'm not spending too much time on. But let's say in the existing focused ultrasound for the brain, the typical accessible area with bulk guided waves, like normal incident waves, the center of the brain, when you try to reach the periphery of the brain, like it gets more tricky because you try to avoid heating of the skull and so on. So we are looking at guided wave transmission, mode conversion, and all that. But primarily, before that, we need to have accurate mechanics of these skull pieces. So this is, I don't think I show a micro image, but yeah, this one has here. If you look at the upper one, these are like micro CT scan with the trabecular, the porous part of the skull piece, and also the cortical tables. So what we try to do is to come up with like these advanced finite element models. Let me go back to previous slide of the segments, and do the speaker excitation, get the mode shapes, first few like audio frequency vibration modes, what should be the cortical tables, and the diploid is what the trabecular porous layer is called. We try to get the elastic parameters so that we can use those in our guided wave models. We run also the guided wave experiments in my lab, and we collaborate with my colleague at CU Boulder. This postdoc, Matteo Mazzotti, did these simulations here. And Etu, my student, does these experiments and also the parameter identification. Again, the merit on, and this is the last slide, merit on using guided waves is that, like, if you are at a relatively low frequency with low speed, most of the wave energy is within the skull. But if you are going to a higher frequency, now look at the right-hand side one, you will see that like when the speed of the wave in the skull is faster, and preferably much faster than the speed of sound in brain, you're going to have the leaking of the wave energy, this guided wave, Lamb wave, into the brain. So that's like there's the possibility of accessing the periphery of the brain. Okay, so with that, I'm not going to bore you with like conclusion items and so on, but like I tried to give you quick examples of like a spectrum of like frequencies of stuff starting from a few hertz all the way to megahertz range. I hope it was useful in one way or another. If there's any questions, I'll be happy to take.
Thank you very much, Alper. We really appreciate it. I think we do have a couple of minutes for questions. If you have a question, just type it into the Q&A box and I will read it out. While we're waiting for those, I guess I'll ask you covered obviously quite a range of applications. I'll ask a very general question. Is there and in particular, but with a particular focus on when I was thinking about the robotic fish, is there any kind of inherent hurdle that prevents miniaturization of that type of
Yeah,
concept?
so that's a good question. And I think the advantage of this kind of, I won't put like, again, much slide, but miniaturization is typically done. There's IPMCs like ionic polymer metal composites, like other soft materials or elastomeric stuff. So when people come up with soft material-based robotic fish, you have good deformation, but like, the common problem in typical actuator for these purposes is the compromise between the deformation level and the actuation force level. So ordinary piezoelectric ceramic gives you, large actuation force but low deformation. That's why we are kind of proud of what this does. So this is perfectly scalable, unless you're talking about like, micro scale. I think even micro scale may have some possibilities, probably not untethered, but you could have micro scale tethered. For us, it's a matter of like being at a reasonable scale. This is the same size as a rainbow trout, and something workable when we partner with like biological people. Again, in the pending Muri proposal, we work with biologists who have these setups like with large, to have these things interact with fish, hopefully, if that gets funded. So we currently have no reason to scale it down. So, but it has the, again, possibility of like, you could easily, so I work with this company that got the license from NASA and the fabricating these things. So I worked with them to make the first waterproof. They put polyester electrode sheets. So these are the first waterproof applications of this stuff. But they also make like smaller versions. Like let's say if this is 8 centimeters length, go down to 1 or 2 centimeters, except the frequency will go up, obviously. What I like about this type of piezo is this is a reasonably large scale. Let's say if you wanted to do a larger fish. So you could both scale up with a careful structural design, or you could scale down. But I would say after some scaling down geometrically, you would rather switch to an elastomeric actuator. Otherwise, the frequencies would just go up.
And we do have another question that just came in. Is there a scaling factor between size and max voltage able to be harvested with piezo transducers? And are any of these harvesting devices robust to harsh environments, such as extreme cold and hot, underwater, etc.?
Yeah, so in terms of like, I should have probably put 1 or 2 slides on that. I jumped into the nonlinear stuff right away. But like we like to talk in terms of power density, how much power output per device volume. I don't think I have any of those here, but the main thing that happens when you scale down, the question of like, how does your amplitude look? Let's say, I mean, the problem may be, I think I was showing you a quick MEMS example here. As you can see here, like these frequencies are not uncommon when you talk about a few hertz. Few hertz is what you have if you want to harvest from, let's say, human gait, like for variable components and so on. For many other applications that humans are exposed to, like up to 100, 200 hertz is fine. But let's say you design a MEMS energy harvester and suddenly your first resonance frequency goes up to 14 kilohertz and your ambient vibrations are at up to 100 hertz. So it's more of like that kind of frequency mismatch that messes up the whole scaling possibility. You could go ahead and do the following. And so for typical power density comparison, you can always assume that I make this guy operate at resonance no matter what. So let's say at centimeter scale, what is the resonance power density of this harvester? And there's this NAMS harvester. What is the resonant power output? In fact, like if you take that kind of approach, if you always assume that no matter what scale, I'll have this guy resonate, you will get advantages at smaller scales for the reason I mentioned. I tried to fit in these few slides, because when you go down to nano scale, you will have substantial enhancement. But the problem is this is now a gigahertz device to get it to resonance. You'll probably, for ambient vibrations, you won't get any power output. So yes, I mean, you can get some scale and loads, but like all I'm trying to say is that like they're not too realistic. You would have to make an assumption. If they are both operating at resonance, it's very hard to get the MEMS cantilever to get to resonate. That's why part of the reason I like this sort of design where rings are light and you have a huge proof mass, then you even with a MEMS design you go down to hundreds of hertz. What was the second question, Dave?
About harsh environments, use in harsh
It's,
environments.
it's a matter of like how you seal it and so on. You do have, I mean, the reason, so like my involvement on this stuff is my Ph.D. 2006 to 2009, and I think there was even earlier stuff in early 2000s, like starting point of piezoelectric energy harvesters. So the reason, for instance, why there is no like off-the-shelf universal piezoelectric energy harvester, this is extremely custom problem. So your design frequency, everything, and how harsh and not harsh, it changes a lot. So with proper sealing, I see no problem, but there's materials issues. Like you may have performance degradation, for instance, like if you're gonna operate. So we mostly like in a lot of these things are like in energy harvesting are NSF, AFOSR, and all that, like or metamaterials for basic science. So the harsh environment questions we mostly receive like for military or DOE or nuclear purposes, like in Sandia projects, like we try to pay attention to those and sealing in applied problems. But overall, I think with careful packaging and sealing, it should be no problem. I think what gets more critical is if you have, let's say, continuous wave operation, whether you're getting some performance degradation so that like your voltage signal may kind of like be affected over long time.
Great. Thanks very much. I think we're actually past the hour, so we're going to end here. I want to thank Professor Erturk one more time, and hopefully we'll see you all in 2 weeks for the next NanoTech seminar. Thanks very much, and stay safe, everybody.
Thank you. Take care. Bye.